Hi, my name is Jeff Coronado from JCSE, and this is a session in Bridging the Gap. Okay, so this one is FCW6-1, um, and we're covering the active soil pressure. Okay, so yeah, what is the active soil pressure on a concrete retaining wall? All right, well, let's take a look at a concrete retaining wall. Let me clear the screen here. And let's just focus kind of on this part of the diagram, if you will, right? So we've got what we have here illustrated is a little concrete stem retaining wall. This is the stem, right? Here's the stem of the retaining wall. Here's your footing. Here's another color. Let's use brown, seems appropriate. So here's the soil. Here's the soil that gets retained by the retaining wall. In this case, we have a slab here on the low side, right? There's a concrete slab, so maybe a walkway or something. So pretty typical um, cantilever retaining wall. Okay, so it is important to make the distinction that this is a cantilever retaining wall, meaning that the top, there is nothing, no other structure at the top of the wall that in any way stabilizes the stem of the concrete retaining wall, right? There's nothing up here that pushes the wall one way or the other. I shouldn't say push, that restrains movement at the top of the wall, right? So this is a cantilever wall. The wall is supported down here at the footing, and that's it. It's not really supported in any other fashion. All right, so that makes it a cantilever retaining wall. Um, okay. So when in a situation like this, soil not only pushes down as would be intuitive, right? Soil has weight to it. So clearly there is a downward push. All of this soil, sorry, wrong way. No, gravity does not go up. Um, Gravity goes down. Yeah. So the soil exerts a pressure downward, but don't really care about that. But the soil also exerts a lateral pressure, which is what we are showing with this triangle. Actually, let me even back up from the triangle. It's really what we're showing. Um, it's really what we're showing with all of these arrows. See all the arrows in green? Okay, so that's the lateral pressure, the sideways push that the soil exerts on the retaining wall. All right, now if there wasn't such a lateral push, if there wasn't, yeah, if soil didn't push on a retaining wall in a sideways fashion, there would be no need for a retaining wall, right? So we could, in theory, how would you feel about removing this retaining wall, removing the stem? Okay, now we just have a steep embankment here of soil, no retaining wall, right? Would you let I don't know, your child? It's kind of how I always used to look at it, and still do. Is something safe or not? Well, would I put my child there? Would I put my toddler there? Would I put a baby? Would I put a baby, let a baby play here with this, I don't know, 5 foot, 10 foot high soil embankment? Eh. So does that mean that you have to have a retaining wall and the soil isn't going to come down? No, but that gets a little bit more convoluted, right? And that's probably something that we'll cover in another session of bridging the gap. It does depend on how cohesive that soil is. But you know what? So yes, the more cohesive the soil is, the better of a chance that the soil will not just cave down, right? But again, if you challenge me to with cohesive soil, let my toddler sit here and play with real cohesive soil. I don't think so, right? I just assume see a nice sturdy retaining wall holding up the embankment. Okay, so so that's the sideways push that we get from soil. Hence why we need retaining walls. All right, moving on here. EFP modeling of the soil pressure. So we model the soil pressure um, by looking at it as if it were a fluid, and hence we get the term equivalent fluid pressure. So no, it's not a fluid, but we create the pressure that the soil exerts on a wall is as if it were a fluid. So we call it equivalent fluid pressure. The equivalent fluid pressure gives us this triangular load, which is larger at the bottom and tapers off to zero at the top of the soil. One of the important distinctions, which is why I stressed that at the beginning, is that this is a cantilever retaining wall. So let's just say hypothetically this were maybe a basement situation where then there is a slab or a floor, sorry. If there were a floor up here, that kind of also restrains the top of the slab, we then would not generate this triangular pressure. Okay, so real important to distinguish retaining walls that are cantilever retaining walls from retaining walls that are restrained at the top. The soil behavior will be different. We're not covering retaining walls in this session where they are restrained at the top. We're only covering cantilever retaining walls. So we're only going to get into the triangular pressure distribution. Okay, and that gets us to this point down here. The triangular distribution applies to unrestrained walls. Okay, so erase this. Unrestrained walls. Notice how the bottom of the triangle that represents the equivalent fluid pressure is at the same height as the footing. Many younger engineers will probably make that mistake, thinking that the triangle distribution starts at the top of the footing and works from there. Because the reason I mention that is because the pressure of this triangle is dependent on the height below the top of the soil. Hence why we have this H here that represents the distance between the top of the soil and the bottom of the footing. So this magnitude, the magnitude of this pressure is dependent on this height. So if you get that height incorrectly, you have underestimated the pressure that you actually have on your wall. Okay, so real important to understand that you're going from top of soil to bottom of footing, and that's the height that you use to calculate the equivalent fluid pressure on the wall. Okay, which might then tell you, you might then ask, well, wait a minute, but if I don't know the footing size when I start, how am I going to calculate then the equivalent fluid pressure? It seems like it's I need one before the other. And you're kind of right. It does become a little bit of an iterative process. You have to kind of make the assumption on what the footing height will be, then calculate your equivalent fluid pressure, calculate the rotation on the wall, and if it doesn't check out, if your footing doesn't check out, you have to increase the footing but increasing the footing will also increase the equivalent fluid pressure. Kind of becomes a little bit of an iterative thing. So let me clear this. So if we do have this triangular pressure here, just be aware that the centroid of this triangular pressure is at the 1/3 point up the height of the triangle, right? So that's where the force resultant, if we were, yeah, that's where the force resultant. So if we were to kind of look at this instead of a triangular distribution and we replace it with just a single force, we would replace it with a force that would be 1/3 of the way up, up from the bottom of the footing. That becomes important for, as I mentioned earlier, for overturning purposes. One of the checks that we have to do is to make sure to ensure that the wall does not overturn, that the whole assembly does not overturn about this point. So we've got this force acting here, which is going to tend to make this whole assembly kind of rotate counterclockwise. And then we have to make sure that the clockwise rotation that's induced by gravity forces acting over here and through the center of the footing, that all of these generate a clockwise, we call that moment, that rotation is moment, that clockwise moment um, exceeds the overturning moment. And building codes specify by how much that needs to exceed. We're not going to get into that in this session. The overturning check, I think we will cover in a subsequent section of the FCW6 series. Okay, I think with that we've covered this, so let's move on here. Okay, what is the numerical value of that pressure? Well, the numerical value is probably, you're probably going to be able to get it in one of two ways. One is through a geotechnical engineer. If your project has a geotechnical engineer, then they'll give you what the active pressure is. If you don't have a geotechnical engineer, then depending on the building code that's in force in where you are doing this retaining wall, you may be able to get some prescriptive values from the building code. So for instance, in this case, this is an excerpt from the California Building Code. This is an excerpt from the 2022 California Building Code. And so here, depending on the soils that we have, there's a table. Actually, there's a table. Let me highlight that here, called lateral soil load. If you're looking at another building code other than the California Building Code, it probably has a very similar name. So whether you're in a region that uses maybe the IBC, or there is another code in force in the jurisdiction where you're designing the structure, where you're designing the retaining wall, but the terminology is probably pretty similar. So you're just looking for lateral soil load, active pressure, anything like that, is what you would be able to use for the equivalent fluid pressure on your retaining wall. And so if you don't have a soils engineer to give you that kind of information, and you have a smaller project, there's a real good chance that the code allows for these prescriptive values. So it kind of depends then on the type of soil, as you can see here. Now, let me see if I can clear this. Zoom in a little bit. Okay, so looks to me like depending on the soil, depending on the kind of soil we have, that's going to dictate what the active pressure is. Well, Jiminy Crickets, I don't know about you, but I have no clue what all these soils are, right? Um, so that puts us in a little bit of a pickle. Okay. Um, so again, we're back to, well, either we can get a soils engineer to tell us what the soil is, or frequently, there may be office standards of where you work that will tell you what active pressure to use. Let me focus on that a little bit. So notice how, let me clear this. Notice how for the first, notice how they're almost in somewhat of a sequence, in order, numerical order, right? The first few pressures that are listed are on the tend to be around 30 pounds. Oh, by the way, this is in 30 pounds, pound per square foot per foot of depth. Yeah. Um, the units here are pounds per cubic foot. Okay. The way the building code here is written, it is pounds per square foot per foot of depth. Not sure that that's more clear to me, more intuitive than just thinking of it as pounds per cubic foot, but it's basically pounds per cubic foot. So anyway, the soils at the top tend to be on the order of 30 pounds per cubic foot. The soils that, as we go down the chart, where can we start? Maybe right here, what I'm highlighting in green, you'll notice the middle soils are more on the order of 45 pounds per cubic foot. And then if I use blue, you can see that the soils more towards the bottom tends to be more along the lines of 60 pounds per cubic foot. So I would say this, your office may have a standard on what active pressure they like to use, probably based on their experience of the region they are in. Um, and if that's not the case, you can probably go to just request that information from your building and safety department. Um, they might be able to give you kind of for that zone what the active soil pressure is. I would say that what I've encountered most frequently is somewhere in the order of 30 to 45 pounds per cubic foot. So, if I didn't have a soils engineer, I don't know, I might do it for 30 pounds per cubic foot. If I wanted to be fairly conservative, I would do it for 45 pounds per cubic foot. I don't think that the norm is to assume 60 pounds per cubic foot. That almost, in fact, you can see here, um, let me use what? Let me use this magenta. If we get into the 60 pounds per cubic foot, the one thing that you start seeing is there is a lot of the word clay pops up, right? So it seems to me like soils that are heavier in clay content, those are the ones that tends to be heavier, and thus resulting in a higher active pressure. So unless we get into those heavier clays, we're probably not going to be in that 60 pounds per cubic foot range. Um, okay, so I think enough on this table. You clear that. So the heavier the soil, the more it pushes sideways. Okay, almost intuitive, almost intuitive. The heavier the soil, the more it's going to push against the wall. If the soil is saturated with water, there will be a greater push sideways. Hmm. Again, almost intuitive, right? It's if this soil were dry, if this soil is dry, change this. So we have this soil, but if it's dry, then there's going to be this certain push. But if the soil is not only has all of that soil, but then think of all the voids that are in soil, right? Inherently, there are voids in soil. So if now there is water that's captured and filling those voids, so intersprinkled in this soil, there is water. Boy, now this gets real heavy, right? This gets real heavy. So that adds an additional component of pressure against the wall. We tend to not design for that water. Our preference is to get rid of the water that's behind a retaining wall. That's the norm. Sometimes, for whatever reason, we may not be able to do that. We can't egress the water out of the soil, in which case, then we have to take into account that it's wet, and that significantly increases then the active pressure on the wall. But our preference is to egress the water out of the soil. Okay, so yes, let's keep the soil against the wall dry. Let's keep the soil dry. So in order to maintain this condition, we need to provide a mechanism to egress the water. One way to achieve this is by installing a perforated pipe. Okay, by installing a perforated pipe. All right, well, what do we mean by that? So one of the ways that we can egress water is by placing a pipe, and usually this is like a PVC pipe. There'll be a pipe with little holes in it. That's why we call it perforated. So a pipe with holes, and it'll be placed kind of here at the base, like on top of the footing. Um, might have drawn this a little bit too large. This might be typically a 4 inch, 4 inch pipe, 6 inch pipe. Um, and the perforations, the little holes in it will be kind of up here. So there'll be like a little, it's just like a little hole, right? Little, I don't know, 1/4 inch. I don't know what it is, half inch hole in the pipe on the top of the pipe, pretty sure. And it'll be every, I don't know, every 12 inches, every 18 inches. So that as the water collects here in the soil and starts to push against the wall, it will migrate down, right? Just through gravity, it migrates down and it'll get into the perforations, going into that pipe, which then the water will run away. Obviously the pipe needs to have a slope, right? So if I look at this if I look in this direction, right, like kind of looking at the length of the wall, I would see, let's say whatever the wall is, maybe 20 feet long, 30 feet long, however long the wall is. And let's say that's a representation of the wall, and this is a representation of the footing. All right, then the pipe is, oops, I don't want to do that. The pipe drawn a little bit at an extreme, but you want that pipe to have a certain slope, right? Because you want the water that collects in the pipe to then run away, you have to put a slope in the pipe so that it runs downhill. And eventually this will empty out somewhere, um, into the curb, maybe into a sump. Um, but the point is you're taking it away from letting it just stagnate there and create lateral pressure on the wall. Okay, so this is one method, the perforated pipe method. This is one method of clearing out the water so that you don't induce active fluid pressure, or so that the active fluid pressure is from dry soil only, not from water that's collecting against the wall. An alternative is to have weep holes with a French drain. Okay, so an alternative to the perforated pipe is to just drill holes in the concrete stem. So again, if we look at the retaining wall kind of in elevation, look at an elevation. So now we're looking, again, we're looking at the wall kind of in this direction. Maybe not. Let's not be in the dirt. Let's say we're not in the dirt, we're outside. We're looking at the wall this way, right? So now here's our stem. And okay, what else would you see there? Maybe your slab, that slab that we have there, right? So here's the slab. And let me use black here. So here you are standing. Let's say it's a 6-foot wall, so you're going to be kind of like that. Yeah, I don't draw people too good, huh? So there's your person. There you are standing, kind of looking at the wall. Here's the important thing. If you're looking at the wall, what you are going to see is every 4 feet, every 6 feet, you're going to see like about a 3-inch diameter or an opening, a core in the wall, which is what's represented by these dashed lines here. Okay, so that way your water, again, builds up here, and as it continues to push and push against the wall and push against the wall, eventually that water will find these holes and push out and get out from behind the wall. Okay, so that's another way. And oh, and by the way, I'm sorry, I'm kind of missing something here. So let me clear this. So there's the part of the French drain. So what's meant by the French drain, right? Well, the French drain refers to this area here. Okay, and I'll clear that for you. But that area there, those are rocks. So that's intended to be gravel. I don't know exactly what the diameter of those pebbles are, but basically it's rocks. Um, And why do we put, well, that's what's called the French drain. And we put the French drain because we want the water. If this were soil, if we didn't put the French drain and we only had soil against the wall, that water could potentially, especially again, if we have higher clay contents in the soil, could potentially struggle to free itself from the voids in the soil. Remember we said that, right? Water is trapped in the voids. If the soil is real cohesive, if it's real clay, then the water might have a hard time getting out of those voids. So even though we've put weep holes down here, the water might struggle to get out of through those weep holes. So we put a French drain, meaning we put all these rocks, we put a certain amount of rock against the wall so that that way the water is trapped in the voids here. But if it starts to want to migrate and put pressure against the wall, it'll get into this layer of rock. And in the rock, there it doesn't get trapped. Then the water freely flows. It'll freely flow against the wall, freely flow down, and freely get out through those weep holes. So that's the value of the French drain. Okay, 2 methods to keep your walls, the active pressure on your retaining wall, free of water surcharge. Okay, all right, real good, guys.